So what is the underlying architecture for LSTM? They are very much a chain-like structure, very similar to RNN, but unlike the pure RNN, where there was just an activation function in the middle between XT and HT, with of course an input coming from HT minus 1, inside the cell, there is more gates and activation functions in order for imparting the memory functionality to LSTM. Very important to note that the activation function here are working in combination with electronic gates. Those of you who have electronics background will understand the notion of these gates, the plus gates and AND gates. These are OR or AND gates, which are electronically measuring digital computation of the OR or AND functions based on the input passed to them. So if you see, the overall output coming out from a single node is not a simple function of HT minus 1 and XT, but it is consisting of a sequence of transformations, including gated outputs after passing on the inputs through different activation functions. Let us assume that this architecture is to be taken for granted, because this has been done after a lot of experimentation and finding out what combinations of gates and what combinations of activation functions are ideal for storing maximum long-term memory. So that's what the whole experiments have been. At the end of it, if you see, the LSTMs have similar to RNN a chain-like structure, but repeating module have basically, instead of a single neural network layer, there are 4 neural network layers with different activation functions interspersed with gates. So think about, there are intermediate digital functions called gates, which are also called as pointwise operators. These could be vector addition, and it could be also that there is a particular line which is going and is broken into 2. So there could be a line forking, which means the content is being copied into 2 different locations and at one time passed on to an activation function and another passed on to a gate. So if you see here, the way it works is there are 4 layers within the individual cell, and there are multiple point operations. And when you talk about concatenation, it's about merging the outputs from 2 different nodes. And if you're copying, that means that there is a split of the same data into 2 copies and sent. So this is the internal operation which is inside the cell. And if you look at, let me put in, if it's possible to put in one slide, I'll see if it is possible, but otherwise we'll go through step by step. So if you look at from the earliest diagram here, we need to understand that cell state is the most important, which is basically the key to what is retained in the memory. Cell state is like a conveyor belt which runs down the chain and some amount of linear interactions in the middle. So if you see, the cell state is CT minus 1 here, it goes to cell CT, which goes through the 2 operators, which is AND and OR. LSTM does have the ability to remove or add information to the cell state, which is controlled by the gates. So as I said, there are 3 trends, right? There are 3 influencing things. There's one long-term trend, then there is the output of previous state, and then there is the current input which is being passed on to it. So gates are the ones which are able to, in conjunction with the 4 different layers with different activation functions, they're giving the actual memory function. So gates allow either information to go through to the next layer, or they retain some and make some information to be forgotten. So they typically consist of a neural network layer and some kind of a pointwise multiplication or some kind of a operation there. So as you know, sigmoid layer outputs numbers between 0 and 1 and describing how much of each component should be led through. Then the sigmoid layer output is determining how much of the data from input should be allowing to be influenced. Then based on that, we have 3 different gates. So the first one is deciding what is to throw away from the cell state. This is what we call as the forget gate. What it does is it looks at ht minus 1 and xt and outputs a number between 0 and 1 for each ct minus 1. So if you see, this is the output we're talking about. If you take ht minus 1 and xt and it passes on to sigma, where it gives the output as 0 or 1. A 1 means completely retain the input, whatever is coming in. Otherwise, if it is 0, forget it, there won't be any effect of this. So for example, if you're talking about predicting next word based on our previous ones, if the cell state wants to include the gender of a person, then the current pronouns can be used. So for example, if you see a new subject, when we say Mary is replaced by say John, so then sigma will become 0 here, so that the previous state is not passed on to the current information. Then basically the previous node, which was the node sigma as output of ht minus 1 and xt, was forget state, depending upon what level of previous data or previous context of previous past data you need to capture is important. If there is no new information, typically the output of sigma would be closer to uh, what we call as 1, where you contain the original information and not change. But suppose if there was a reference to something like say Mary earlier and now it's become John, then the output of sigma could be 0 because it wants to remove the context from earlier Mary to John. So any future it will refers to now the new subject, which is John. So forget information is used for forgetting the older subject. And once you've obtained the forget gate, the next gate is what we call as input gate. What this does is it decides what new information we're going to store in the cell state. First of all, there is a sigmoid layer. Then there is a tan hyperbolic layer, which creates a candidate values which need to be added to the current step. Then we combine both of them to create an update to the cell state. So in our language model, we would want to add gender of the new subject to the cell state to replace the old one we're forgetting. So if you see what we're doing here, we're taking a copy of the original, which we had sigma. Then we pass it to the gate, and then we also take the tan hyperbolic function of the previous ht minus 1 and xt and add corresponding bias. Now we also need to understand that here the cell ct minus 1 is updated to a cell ct, where whatever we decide to do by adding on the forgetting state and adding on the new components of the inputs which we want to add to the current state, we have added here. So in that sense, the second state, which is a combination of two hidden layers, which is sigma and tan hyperbolic, in combination with the architecture, what it does is it combines the previous forget output and selective selection from the current new additions it wants to update. It's what it gives us the candidate value to pass on to the current cell to memorize. So what we would do in case of language model is we would drop the old subject gender and add the new gender, which is basically going to be the final cell state depending upon the level of output of the forget gate and what incremental component of the input state you're going to add to it. Then the final one, which is basically what we decide is, okay, you're done forgetting of the old context, you added something from the new, some part of it you're added to update it. The output is basically the final cell state, which will be a sigmoid layer, which decides upon how much of the output of combination of forget and input gate you should be remembering as a cell state. So, for example, in the language model, since it saw a subject, it might want to output information related to the verb. That is what is coming next. Or, for example, it might output whether the subject is singular or plural, so that we know that when a verb is conjugated to it, what is coming next. So here, if you see what we're talking about is we're taking the output of forget gate and passing on to the tan hyperbolic function to understand what should be the final output, which is from the state which is already captured the forget and the input gates. This is what is going to give the output. So if you see, I didn't want to bore you with too much depth, but let's think in terms of the architecture having been developed after a lot of perturbations and combinations of different gates, etc., so that we are able to take into account what are the requirements for long-term dependencies. So the long-term dependencies require, as I said, the requirement for three things. One is depending upon what is there in the originally in the current state, that is dictated by forget gate. Then how much of the, that's what we call as the trend. Then we can call as seasonality, which is the local dependence on the previous gate. That's what is done by the input gate. Then we want to see the input influence on this to be carried forward in terms of memory. That's what is called the output gate. So if you see broadly, the time series models of these three are being captured inside the architecture of a single LSTM. And if you look at the example of a forget gate, let us say text prediction problem. Let us say we say David lives near to the school. Harry is really lazy. If you see, earlier subject was David, whereas after the full stop is talking about Harry. So suddenly forget gates forgets about David and will take forward the selective input, which is input coming from Harry, will be formed as the input. Now, let us say the text problem once again. Let's say David spoke to me over phone and said that he likes horse riding. He will be coming to visit us next week. So here, important information is he likes horse riding and he will be coming to visit us. Whereas it's not necessary whether it is said over face-to-face or over the phone. So input gate will have corresponding digital vector, which is going to ignore the fact that over the phone, but whereas it will continue to forward the vector corresponding to horse riding and visiting us next week. Then in terms of output gate, it's not that all the output of the input gate is required to be output. For example, Rachel practiced tennis every day. The first prize went to. In the above sentence, first prize can only go to a noun. Since LSTMs can remember the context, it can predict that it should go to Rachel. So selecting useful information from the current cell state and showing it as output is what is done by output gate. So the combination of these three is what gives the power of long-term and short-term memory overcoming the vanishing gradients problem for LSTM. So if you see, one important element you got to understand is that the architecture of LSTM is so powerful that today nobody talks of RNN per se. Whenever people talk about modeling any recurrent network problem, it is always converted to a what we call as LSTM, and unless otherwise specified, when we talk of RNN, we will by default refer to LSTM as the corresponding cell architecture. And even when we talk of complex architecture, like say bidirectional LSTM, that's what we primarily refer to, though there may be pure bidirectional RNN also. But important thing is, in the context of recurrent neural networks, unless otherwise specified, we will most commonly be dealing with LSTMs as the default choice of architecture for doing any prediction problem for neural networks based sequential problems.